folks, today we are going to focus on intermolecular forces, that is, the forces that exist between different molecules. Again, my name is Jaylan Bio, excited to be here today to run you through some AP chemistry focused on intermolecular forces. If we take a look at our student learning objectives for today, hopefully by the end of this video you will be able to explain all of the different intermolecular forces possible, and then also be able to explain how these forces are possible between different types of molecules. Now, I know that you've talked a little bit about this before, but we're going to dive a little bit deeper into what causes some of these forces and the strengths related to them. So what are intermolecular forces? Well, they are forces that exist between two or more different molecules. Now, these forces play a huge role in many of the properties of molecules, such as the ability to perform adhesion, cohesion, things like boiling point, vapor pressure, those types of things. Intermolecular forces are typically weaker than things like ionic or covalent bonding, which are intramolecular forces. Remember that intramolecular forces are within the same compound, whereas intermolecular forces are forces between different ones. The stronger the intermolecular forces, the stronger the interactions that hold the substance together. Therefore, the lower the vapor pressure of a liquid at a given temperature, and the harder it is to vaporize a substance. So you have to imagine a rigid container, and that rigid container holds some liquid in it. The stronger the intermolecular forces, the less likely it is to evaporate or become a gas. If it has low intermolecular forces, it becomes a gas more readily. As a result, the pressure inside of the chamber is going to be higher because more of the particles went from a liquid state into a gaseous state. So kind of keep these things in mind, is that intermolecular forces explain a lot of different properties about different chemical compounds. Now, London dispersion forces are typically considered the weakest force, but they may be the strongest in very, very large molecules, in particular biomolecules. London dispersion forces are intermolecular forces that occur as a result of Coulombic attraction between temporary fluctuating dipoles. So you probably know from modern atomic theory that electrons can exist in three-dimensional regions called orbitals. Well, in some instantaneous instances, those electrons all may be located on one side of the atom when compared to the other. That results in a dipole being produced, which you can see on the bottom. If all those electrons are on the right-hand side of the atom, that produces a slight negative charge associated with that side of the atom. Whereas if there's slight negative charge on one side, the opposite side will have a slight positive charge because the electrons are not present there. The dispersion forces increase with increasing size of atoms. Makes sense because they have more electrons and therefore can have stronger London dispersion forces. And with highly polarizable atoms. Now, when I refer to a polarizable atom, it just simply means an atom that is larger and has a large electron cloud. If it has a large electron cloud, those electrons are more likely to shift in one direction and be over on one side of the atom when compared to the other, creating that weak dipole moment. Now, keep in mind that London dispersion forces occur in every single type of molecule because, well, all molecules and atoms have some form of electrons. Now, if you take a look down here at the bottom, as the molar mass increases, the number of electrons increases. Therefore, the strength of the dispersion forces will increase. If you look down going to the noble gases, you can see the size of the atom increasing, and therefore the London dispersion forces will increase as well. The stronger the attractive forces between the molecules, the higher the boiling point. So you can see the boiling point increasing as the radius and the size of the atom increases as well. So when we talk about dipoles, dipole is literally a molecule that has two poles, positive and negative. And this is due to the uneven distribution of electrons on the molecule. Now, dipoles can exist in bonds as well as molecules. Bond dipoles do have the ability to cancel out. So if we look at CO2 down at the bottom, we do have polar bonds. There's a difference in electronegativity. Therefore, the bond is considered polar. The dipole arrow points towards the highest electronegativity. So for example, in CO2, the dipole arrow points to the left in the left bond and the right side on the right bond. But because those two dipoles are exact opposites of each other, they actually end up canceling each other out, which results in the overall dipole moment being zero. CO2 is a nonpolar molecule. If we take a look at H2O, we draw our dipole arrows here because oxygen's more electronegative than hydrogen, and they don't cancel out. The left and right vectors will cancel out, but there's two up vectors that are associated with this. As a result, it does have a slight dipole moment, which makes water polar. Now, inducing a polar substance into a nonpolar substance can induce a dipole into the nonpolar substance. That's called a dipole-induced dipole. So if we take a look at the bottom here, a molecule of water is introduced to a molecule of oxygen. Now, the isolated oxygen is nonpolar. You can induce a dipole in there because the water molecule has a permanent dipole. The electrons on the top are relatively negative. They are going to force the electrons on the opposite side of oxygen away from that side, thus creating a positive dipole that's attracted to the negatively charged electrons. The opposite side then becomes relatively negative because it has more electrons than the opposite side. So by introducing a polar substance into nonpolar material, we can actually induce a dipole. Oh, also keep in mind, I am going in order from weakest intermolecular force to strongest intermolecular force, at least on an individual level. Dipole-dipole interactions are present between polar molecules. The interaction is dependent on the strength and the dipoles and the orientation. So we have HCl here. Chlorine is far more electronegative than hydrogen and therefore has a relative negative charge. The hydrogen has a relative positive charge. The strength of the dipoles is purely dependent on the difference in electronegativity between the two atoms that are present. The negative of one is going to be attracted to the positive of another. These interactions are much stronger when compared to London forces in similar molecules, particularly ones of similar size. Now, ion dipole forces of attraction are present between ions and polar molecules. So you can take an ion, such as sodium, and place it into water, and you have strong attractive forces between the water molecules and the sodium ion. The sodium ion has a positive charge, so notice that all the water molecules are oriented to where the oxygen is attracted to the sodium. It's because the oxygen has the relative negative charge on water, and sodium has the relative positive charge. The relative strength of these is determined by considering the sign of the charge and the strength of the ion. So we look at the signs and the strength of the ions. That helps us determine the strength of the ion dipole attraction. The last intermolecular force I want to focus on is hydrogen bonding. And hydrogen bonding is a strong type of intermolecular force. In particular, it is a dipole-dipole force that exists when a hydrogen atom is bonded to a highly electronegative atom, nitrogen, oxygen, or fluorine. The large difference in electronegativity results in a large dipole, which results in very strong ion forces. Water is an example of this. Water has a hydrogen that is covalently bonded to oxygen. Because of the very large difference in electronegativity, that gives the oxygen even more of a negative charge and the hydrogen more of a positive charge. Therefore, the large difference in electronegativity results in the large dipole, which results in those very strong intermolecular forces between water, which allows for all the very unique properties that water has. Hey guys, that's all I got for you guys today. Hopefully we're able to take this information and apply it to lots of different stuff. We'll hopefully do a lab over this. This is JLand Bio. Make sure you like and subscribe, leave a comment down below, and make sure you shop that merch. Have a great day, guys. We'll talk to you later. Bye-bye.